This video is going to serve as an introduction for much of the rest of the chapter. So here we're going to talk about, in general, about nucleophilic addition reactions to aldehydes and ketones. And then for much of the rest of the chapter, we'll be looking at specific examples of these nucleophilic addition reactions. So we've already seen a number of different ways that we can prepare aldehydes and ketones. This chart is a summary of the ways that we've learned to make aldehydes. And so I'm not going to go through these in detail, but if you don't remember them, you're going to go back and review them. Earlier this semester, we learned how to make aldehydes from the oxidation of primary alcohols. Last semester, we learned how to make aldehydes from either the ozonolysis of alkenes or the hydroboration oxidation of terminal alkynes. Similarly, we learned a number of ways to generate ketones. Earlier this semester, we learned about oxidation of secondary alcohols. And then last semester, we learned about ozonolysis of alkenes, and then acid-catalyzed hydration of terminal alkynes. And then also this semester, last chapter, we learned about Friedel-Crafts acylation, which is another way to make ketones. So when we have a carbon double bonded to an oxygen, this is called a carbonyl group, or oftentimes you'll hear it referred to as a carbonyl. One of the most important features of this carbonyl group is that the carbon is extremely electrophilic. And this is due to a combination of resonance effects and then also just straight up induction effects, because the oxygen is so much more electronegative than the carbon. And so both of these effects combined make this carbon an extremely good electrophile. So a common feature of the nucleophilic addition reactions that we're going to be talking about in this chapter is the nucleophile is going to attack the carbon of the carbonyl group, and in doing so it forms a new sigma bond between that carbon atom and the nucleophile, and the pi bond connecting the carbon and oxygen becomes a lone pair on the oxygen atom. And then also significantly, both the geometry and the hybridization changes. When we have this triple bond in the carbonyl group, it's sp2 hybridized, and that carbon is trigonal planar. After it's attacked by the nucleophile, the new geometry is tetrahedral, and we now have an sp3 hybridized carbon atom. Now, for the most part, aldehydes are generally more reactive towards nucleophiles than ketones, and there are two factors that lead to this. One is steric effects. When we have the ketone, the carbonyl carbon is attached to two other carbons, right? And so there's more crap to get in the way. In the case of an aldehyde, it's only attached to one other carbon. The hydrogen is much less has much less steric interactions than a carbon atom with a bunch of stuff attached to it. So the aldehyde is just more easily accessible to the nucleophile. The second factor is electronic effects. So we've talked a couple times about the fact that alkyl groups are electron donating. So we first encountered this when we talked about the stability of carbocations, and then it was also a big factor when we talked about the electrophilic aromatic substitution reactions that we talked about last chapter. Right, through hyperconjugation, alkyl groups can donate electron density. So they help negate the partial positive charge on the ketone better than they do on the aldehyde, because on the ketone there are two alkyl groups to donate electron density. In the case of the aldehyde, there's only one. And so that reduces the electrophilic nature of the ketone a little bit, because as it gets electron density donated to it, it's a little bit less partial positive. Because the electron donating is less effective with just the one alkyl group, that leaves the partial positive charge on the aldehyde being larger, leaving it as a more effective electrophile. A common feature of these nucleophilic addition reactions is that they generally require that we either be in acidic or basic conditions to help catalyze or speed up the reaction. And very often it's the case that the strong nucleophiles mean the reaction is going to occur under basic conditions. Grignard reagents are one example of that. The other deal with Grignard reagents, they are themselves strong bases, so that's why basic conditions are required. And in fact, if we're in acidic conditions, those acidic conditions destroy the Grignard reagent, and so those reactions aren't going to work. But then if we consider some of the other strong nucleophiles, right, hydroxides are very basic, hydrides are very basic, so just the nature of the strong nucleophiles often means that we'll be in basic conditions. So the mechanism for these nucleophilic addition reactions under basic conditions is similar whenever we're under basic conditions. And it starts with a nucleophilic attack. So the nucleophile comes in and adds to the carbonyl carbon. The pi bond becomes a lone pair on the oxygen. And then that's followed up with proton transfer, where a proton donor will give up its proton to what became the negative oxygen. If we had a nucleophilic attack where we had a negatively charged species at this point, we would need to finish up the reaction with an acidic workup. Very often when we have weak nucleophiles, they run best under acidic conditions. And the two steps in the mechanism for the nucleophilic attack under acidic conditions are the same, they're just in a different order. On the last slide, we saw under basic conditions, the nucleophilic attack attacked first, and then the proton transfer happened. In the case of acidic conditions, we first have the proton transfer, and then we have the nucleophilic attack. The reason we get the proton transfer first is because if we have a weak nucleophile, by doing the proton transfer first, that makes this compound now a much stronger electrophile than our starting compound. So while this might not have reacted with a weak nucleophile, after protonating it and making this now a much stronger electrophile, this is willing to react with the weak nucleophile where this one was not. And this just really reiterates what I said on the last slide. Oftentimes we need acidic conditions when we have weak nucleophiles. Right? Two examples of weak nucleophiles would be water or an alcohol. We need these acidic conditions because we need to protonate our ketone or aldehyde first to make it a stronger electrophile than the starting material. So one of the features of these reactions we'll be talking a lot over the course of this chapter is the fact that these nucleophilic addition reactions are equilibrium in nature, meaning they often don't go all the way to completion. And depending on the conditions, we may have reactant-favored or product-favored reactions. So one thing that can influence that is the ability of the nucleophile to act as a leaving group. So in this reaction, the reactant is actually favored because our nucleophile in this case is a very good leaving group. Right? Cl- is not a strong base, so it's very stable in solution, and so Cl- acts very well as a leaving group. When the nucleophile also acts as a good leaving group, very often the reactants are going to be favored. On the other hand, some examples of strong nucleophiles that are bad leaving groups, these things are generally strong bases, right? Grignard reagents, hydroxides are all strong bases, meaning they're not very stable, and so they're not particularly good leaving groups, and then very often reactions with these species will favor the products. All right, so in this video we've been talking generally about nucleophilic addition reactions, and for much of the rest of the chapter we're going to be looking at now specific examples of nucleophiles. I think this is a pretty good video to come back and review, especially at the end of the chapter, to kind of see how everything ties together. And these two mechanisms that we've learned under acidic or basic conditions, we're going to be coming back and seeing that the mechanisms for all of these other nucleophiles follow those same general patterns.